Today's lesson's on balancing complex redox equations as well as redox titration calculations. So let's go over the rules for balancing a complex redox equation. So these are, I don't know if rules the right word, maybe steps is better. First step is to separate the equation into two half reactions. So you'll be given some unbalanced net ionic equation. And so you want to separate into two half reactions where one is an oxidation and the other is a reduction. So they're known as oxidation half reactions and reduction half reactions. So remember that when a substance is oxidized, it loses electrons. Those electrons are shown on the right side of the equation. When a substance is reduced, it is gaining electrons, and those electrons that are gained are shown on the left side of the equation. Next step is to balance the number of atoms of the element whose oxidation number is changing. So what you want to do first is go through each substance, determine its oxidation number, and see what is being oxidized and what is being reduced. In this class, most likely the substance being oxidized and the substance being reduced are things other than hydrogen and oxygen. Not to say that hydrogen and oxygen can't be oxidized or reduced, but usually it's something else that the reaction is occurring between. So check something else first, and then if they're not changing, then check oxygen and hydrogen. Speaking of oxygen, you're going to balance the number of oxygen atoms by adding not O, not O2, not O minus 2, but adding water. So these redox reactions occur in solution, and so we have water present, so we can use water to balance the oxygens. Anytime you add water, that means you're going to have to balance the hydrogens. We're going to balance hydrogen not by adding H or H2, but rather by adding H+. We'll assume that the reaction occurs in an acidic solution unless it is stated otherwise. If the reaction occurs in a basic solution, I'll show you some steps for how we balance in that situation. So add H+ to balance the hydrogens. Next, by this point, we will have mass balance. Our next step is to balance charge. We balance charge by adding electrons. So we need to look at the charges of each of these substances on the left and right side of our equations. And we're going to balance charge by adding electrons. You will add electrons to the more positive or less negative side so that the charge is the same on both sides. Next step is you're going to multiply one or both half reactions as necessary so that the electrons cancel. So it makes no sense to have any electrons in your overall equation. It makes no sense for there to be more electrons gained by one substance than lost by another. So those electrons have to be the same. They have to cancel. And so sometimes you need to multiply one or both half reactions by some number to get those electrons to have the same number. Next, we'll combine the equations, add the equations. In doing so, those electrons cancel. Step number 8, if the reaction occurs in a basic solution, so we're going to do everything we've done so far, we have some additional steps. You're going to add the same number of OH minus as there are H plus ions. Here's the key though, to both sides of the equation. So let's say you have two H pluses on the left. If the reaction occurs in a basic solution, you'll add two OH minuses to the left and to the right side. On the left side, where you have both H plus and OH minus, you're going to combine those to make water. Undoubtedly, you're going to have waters on both the left and right side, so cancel any extra waters if there are any. Last step, check. Check to see if you're right. Check both mass and charge. If both mass and charge are balanced, then you know the equation is balanced. All right, so let's take a look at some examples. Go to page 385. I'll walk you through an example there, and then I'll actually do the next one with you. So 1110 at the bottom of the page says you have a reaction between iodine and thiosulfates, sodium thiosulfate Na2S2O3. It says the iodine oxidizes the thiosulfate ions to tetrathionate ions, and then the iodine is reduced to iodide ions. So take a look down at the bottom of the solution. We have our unbalanced net ionic equation. First step is to separate into two half reactions. So one of them has iodine. That's the first one that the book balances. So there's no oxygen to balance, so we don't need to go through the process of adding water, so we can just balance the iodines by putting a 2 in front of I minus. Total charge on the left is 0, total charge on the right negative 2, so we need 2 electrons on the left to balance charge. And then the sulfur half reaction, we need to balance the sulfur atoms first. There's 2 on the left, 4 on the right, so put a 2 in front of the thiosulfate, S2O3. And then we have oxygens already balanced, so no need to add water, no need to add H+, but we do need to balance the charge. Next, total charge on the left is negative 4. There's 2 thiosulfate ions, each with a negative 2 charge, that's negative 4. And then 1 tetrathionate ion on the right, charge of negative 2, so we need 2 more electrons on the right side. Turn the page. Combine our half reactions, and we end up with our balanced equation. All right, it gets a little trickier when we have to add the waters and do all that stuff. So take a look at 1111. In fact, I'm going to walk you through that. So it says permanganate ions oxidize iron 2 to iron 3 in sulfuric acid solution. The permanganate ions are reduced to manganese 2 ions. So let's start off with our unbalanced equation. So the iron is going from an oxidation state of +2 to +3. So the iron is being oxidized. Permanganate is a very common oxidizing agent. So let's look at the manganese. In permanganate, manganese has an oxidation state of +7. And over here has a oxidation state of +2. So not -1. Look at an oxidation state of manganese, +7. Goes from +7 to +2 because the manganese is being reduced. All right, so let's separate this into 2 half reactions. We have one that has iron on both sides. And then we have one that has manganese on both sides. All right, so let's start with our iron half reaction. Mass is already balanced. We have 1 iron on the left, 1 on the right. We need to balance charge. +2 on the left, +3 on the right, a difference in charge of 1. So that means we need 1 electron. And we said that the iron is being oxidized. So remember, in an oxidation half reaction, the electrons that are being lost go on the right side. Confirm that the charge is the same on both sides. We have +2 on the left, +3 plus -1 is +2 on the right. Charge is balanced. Now let's take a look at the manganese half reaction. We'll start by balancing the manganese atoms. We have 1 manganese on the left, and we have 1 on the right. So manganese is already balanced. Our next step is to balance oxygens. We have 4 oxygens on the left, none on the right. So to balance oxygen, we're going to add water. 1 water per oxygen we want to balance. We need 4 waters. Next step is to balance hydrogen by adding H+. So we now have 8 hydrogens on the right. So we need 1 H+ for each hydrogen on the other side. So we have 8 H+. Total charge. Let's balance the charge. What is the total charge of everything on the left side? Be careful about the coefficients and the charges of those ions. On the left side, the total charge is +7. So we have 8 + 1 ions, 1 -1 ion. So that gives us the total charge over here of +7. On the right side, we got +2 and 0. So total charge +2. This time, the difference in charge is 5. Remember we said in a reduction half reaction, the electrons that are being gained go on the left side. So let's put 5 electrons over here. We have 5 electrons gained, only 1 electron lost. That does not make sense. The electrons gained must be equal to the electrons lost. So we're going to multiply our iron half reaction by 5. Multiply everything in that half reaction by 5. So we have 5 electrons lost, 5 electrons gained. Those cancel. Let's bring everything down that's not crossed off. Whoops, we have 5 iron 2s plus 8 H plus 1 MnO4 minus makes 5 Fe plus 3 plus 1 Mn plus 2 plus 4 H2O. Check mass. 5 ions on the left, 5 on the right. 8 hydrogens on the left, 8 on the right. 1 manganese on the left, 1 on the right. 4 oxygens on the left, 4 on the right. Total charge on the left side. What do you see on the left? I see 5 times 2, that's 10, plus 8, that's 18. And then we have a minus 1, so that's 17, plus 17 on the left. And on the right side, we got 5 times plus 3, that's 15, plus 2, 17 on the right. Charge and mass are both balanced. This equation is balanced. All right, so let's next take a look at the exercise. Number 58 on page 395. So again, we're given the unbalanced net ionic equation. Don't worry about the H plus and the H2O. You can ignore those. We'll take care of H plus when we balance. We'll take care of H2O when we balance. So we have manganese in one half reaction. We have carbon in another half reaction. So go ahead and pause the video and write the balance equation for that reaction. Pause now, please. All right, so here's what we end up with. So the manganese half reaction is the same as our last example, exactly the same. Be careful here. We have 2 carbons on the left. A common mistake is to forget to balance carbon first. So we got to put a 2 in front of CO2. And then it looks like our oxygens are already balanced. Charge, 2 electrons. So notice we have 5 electrons gained, 2 electrons lost. Least common multiple is 10. So we multiply the top half reaction by 2. I usually don't like doing this where I put in parentheses, but I want to do this for just to show you. Normally, I would change the coefficient of every substance. So make this a 10, 16, 2, 2, and 8. Likewise, for the bottom half reaction, I would distribute that multiplier to each substance. So 5 of those, 10 of those, and 10 electrons. 10 electrons gained, 10 electrons lost. Those cancel, and we end up with this. And if you check, both mass and charge are balanced. All right, let's go ahead and go to 1113 on page 388. Read along with me, please. In basic solution this time, hypochlorite ions oxidize chromite ions to chromate ions, and the hypochlorite is reduced to chloride. Right, the balance equation for this reaction. Now, I'm going to show you a different way than the book does it. So, actually, let's do this. Go ahead and let's start off with the unbalanced equation. I'll write it up here, and we'll do it in this space. All right, here's what I want you to do. Go ahead and balance this equation as if the reaction occurred in an acidic solution. So please do not copy what the book does. They're doing it differently. And then when we resume, I'll show you what to do when the reaction occurs in a basic solution. So balance this equation as if the reaction occurred in an acidic solution, just like we did in the last example. Pause the video while you do this, and then I'll show you what to do about it being in a basic solution. Pause now, please. So if the reaction occurred in an acidic solution, this would be our balanced equation, but we have some additional steps since the reaction occurred in a basic solution. So going back to your notes, it says if the reaction occurs in a basic solution, you're going to add the same number of OH minus as there is H plus to both sides. So I'm going to add, I'm out of room here, so I'm going to add 2 OH minuses there. And I don't know if I can squeeze that in, so I'm going to add it here. 2 OH minuses to the left. Now notice on this side we have 2 H plus and 2 OH minus. That's going to make 2 waters. And I believe we have water on the other side. We have 2 waters on the right, 1 on the left. So this 1 on the left is going to cancel with 1 on the right. And so we end up still with 1 on the right. So we have 2 OH minus plus 2 CrO2 minus plus 3 ClO minus makes 2 CrO4 minus 2 plus 3 Cl minus plus H2O. So hopefully you're able to keep track of everything in there. There's a lot of crossing off and canceling. And hopefully this was what you got. If not, please let me know. We can go over it in class. All right, before we move on to the next section, a question for you. What are the reactants in an acid-base titration? So some of you just performed an acid-base titration. What were the reactants? Well, in acid-base titration, one of the reactants is an acid and the other is a base. Well, how about in a redox titration? What are the reactants in a redox titration called? Well, one of them is an oxidizing agent and the other is a reducing agent. So interestingly, for redox titration, we don't use indicators because many of the chemicals involved are colored themselves. So it's important to know the colors of these common substances that we use in redox titrations. Permanganate is a common oxidizing agent, as mentioned before. It is purple, dark purple in solution. Chromates is yellow in solution. Also a good oxidizing agent, as is dichromate. Dichromate is orange in solution. And dichromate reduces to chromium-3, which is green in solution. So be familiar with these substances and the colors of their solutions. All right, let's take a look at 11.4 on page 389. It says, what volume of 0.0200 molar potassium permanganate solution is required to oxidize 40 milliliters of 0.100 molar iron 2 sulfate in sulfuric acid solution? And you can see an example of that kind of titration at the bottom of the page, where we titrate to kind of a coral, I don't know what color you call that. It's not really pink. More of a salmon, I think, is a color we use. The word we use to describe the color, salmon color. So take a look on the next page. Our first step is to write the balanced equation for the reaction. And so just like we did before, so we can see that's just below where it says solution. And then we treat it like any other stoichiometric calculation. We know the volume and concentration of the iron 2 solution. Sulfate is just a spectator ion, so is potassium. So knowing the volume and molarity of the iron 2 solution, we can use that to find moles of iron 2. From moles of iron 2, we can use the balanced equation to find moles of permanganate. So there is a 1:5 ratio of permanganate to iron. And then once we know the moles of permanganate, we can use that and the molarity to find the volume. So we need 40 milliliters of that solution. All right, let's go ahead and turn to page 395. I'll have you do a practice one on your own, number 62. Go ahead and pause the video. Make sure again to write the balanced equation for the reaction. It's the same as that last example. But for practice, you should balance, not that one per se, but any other that you're given. Pause now, please. All right, here's our setup. Got our balanced equation. Again, given the volume and concentration of the permanganate solution, you can use that to find moles of permanganate, moles of iron 2, that is. And then once we know moles of iron 2, we can use that to find moles of permanganate using the mole ratio from the balanced redox equation. Take our moles divided by the molarity, and that will give us our volume. So again, it's 3.52 milliliters of permanganates, but there's a 1-to-1 ratio. I didn't include that conversion factor here, but you could put that. 1 mole KMnO4 over 1 mole MnO4 minus. That comes from the balanced dissociation equation for potassium permanganate. It's a 1-to-1 ratio, so 3.52 milliliters of potassium permanganate. All right, number 63. Go ahead and give that one a shot. Again, start off with the balanced redox equation and then perform the calculation. Go ahead and pause the video now. So there's our balanced equation. Make sure you got that right. Again, we're taking the volume and concentration of the sulfite solution. So notice there's a 1-to-1 ratio of sulfite ions to sodium sulfite. And then we convert that to moles of dichromates using the balanced equation, 1-to-3 ratio. Take that divided by the concentration of the dichromate, 0.213, and that'll give us volume. Notice you'll get your volume in liters. I didn't mention that in the last example. You'll get your volume in liters That's a really small number here again, so go ahead and convert that to milliliters. And one more time, we have a 1-to-1 ratio of dichromate to potassium dichromate. And if that was not the case, then we'd have to take that into consideration in our calculation. All right, we have another example to look at, 1115 on page 391. Same idea, except this time we're calculating molarity. So same approach, we're given the volume and concentration of one solution. We can use that to find moles of that substance. Using our balanced redox equation, we can find moles of a different substance. So in this case, we're going to take the moles and divide it by the volume to get molarity. So go ahead and try one like that. It's number 67 on page 395. Go ahead and pause the video and work on that now, please. So sound like a broken record, given the volume and concentration of one solution. In this case, the thiosulfate solution, S2O3-2. We can use that to find moles of thiosulfate. Using the balanced equation, we can go from moles of thiosulfate to moles of copper 2 ions. And then 1-to-1 ratio of copper 2 sulfate to copper 2 ions. And then we can convert to grams of copper 2 sulfates. It's something like 1-something grams of copper 2 sulfate in that total 4.115 grams of the mixture. Ran out of room, take that, multiply by 100, we get 27.95% copper 2 sulfate, and the rest would be potassium iodide. All right, that concludes this unit. Let me know if you have any questions. Thanks for watching.